All right, today we're going to take on a concept that feels, well, limitless infinity. We're going to see how a simple shift in perspective, looking at numbers not just as quantities, but as actual points in a geometric landscape, can give us the power to do what sounds impossible, to actually tame infinity itself.
So let me ask you this. What if infinity wasn't some abstract idea at the unreachable edge of everything? What if it was just another point? A specific location you could actually pinpoint on a map? I know, it sounds like a total paradox, but that's the exact map we're about to build together. And the solution to this puzzle? It's a stunningly elegant idea called the Riemann sphere. It's a model that takes the entire, infinitely sprawling plane of numbers and somehow wraps it perfectly onto the surface of a sphere. To really get how that works, though, we first need to build a new set of tools for navigating this plane. Okay, so before we can wrap this infinite plane, we need to understand the map itself. And this means we've got to move beyond that familiar grade from high school math and into a new, much richer landscape, the complex plane.
You see, on the left, you've got the good old Cartesian plane. A point is just a pair of coordinates, right? But on the right, in the complex plane, things are different. A point isn't just a location, it is a number, one that has both a real part and an imaginary part. They're not two separate axes anymore, they're two dimensions of a single thing.
Now, on this new map, just saying go over x and up y isn't the most powerful way to think about it. Instead, we're going to use a system that feels a lot more like navigation in the real world, distance and direction. First up is distance. In the complex plane, we call this the modulus. It's really simple. It's just the straight line distance from the center, the origin, out to our number. It tells us its size, its magnitude. Think of it as the first part of our new GPS coordinates, exactly how far to go. And the second part of our GPS, that's direction, which we call the argument. It's just the angle that our number makes with the positive real axis. So, with these two pieces of info, the modulus for distance and the argument for direction, we can pinpoint any complex number perfectly. And this is where things get truly incredible. Because by defining numbers with distance and direction, we unlock their hidden superpower. It completely changes everything we thought we knew about a basic operation, multiplication.
Get ready for this, so here's the big secret. When you multiply two complex numbers, you're not really doing some abstract algebraic calculation. Nope, you are performing a clear geometric action. You are rotating and you're scaling. That's it. All that complexity in the algebra just boils down to those two simple motions.
This is Euler's form, and it illustrates the rules so beautifully. Think of it like a recipe. To multiply two numbers, you simply multiply their lengths, their moduli, those r values. Then you just add their angles, their arguments, the theta values. It's an unbelievably simple and powerful geometric rule. So now that we understand this beautiful geometric dance of complex numbers, we have the exact tools we need to solve our original puzzle, how to wrap an infinite plane onto a finite sphere, and finally give infinity a proper address. The mechanism that does this is a genius method called stereographic projection. It creates this perfect one-to-one link between every single point on our infinite complex plane and a corresponding point on a sphere. Well, almost every point. It leaves one tiny spot on the sphere open, for now. Here's how it works. Just imagine placing a sphere so its south pole is just resting on the origin of our complex plane. Now pick any number you want on that plane. To find its new address, you draw a straight line from that number all the way up to the north pole of the sphere. And the one unique point where that line pierces the surface of the sphere, that's its new location. And you can do this for every single number out there. Points that are close to the origin, they map onto the southern hemisphere. Points farther out, they climb up the sphere past the equator. The entire, endless, infinite plane gets neatly and completely mapped onto the surface of this one single sphere. So what about that one point we left out, the North Pole itself? Well, here's the magic. As you pick numbers on the plane that are farther and farther and farther away, heading out toward infinity in any direction, their points on the sphere climb higher and higher, all getting closer and closer to the North Pole. The North Pole becomes the single, unified destination for the entire concept of infinity. It's no longer just a direction, it's a place. And just like that, we've done it. By changing our perspective from pure algebra to geometry, we've taken this wild, untamable concept of infinity and given it one neat single address. But this is so much more than just a cool mathematical party trick. Why does this actually matter? Well, this idea has some really profound consequences. It lets mathematicians finally make sense of forbidden things like 1 divided by 0 by rigorously defining it as a trip to the point at infinity. It's a cornerstone of a huge field called complex analysis, making really messy functions behave beautifully. And this isn't just abstract theory. It has very real applications in modern physics, from quantum mechanics with the Bloch sphere to things like twistor theory. But really, what it shows us is how a change in perspective can solve problems that seem completely impossible. And that, of course, leaves us with one last fascinating question. By visualizing numbers in a totally new way, we solved a problem that once seemed absolutely impossible. It really makes you wonder, doesn't it? What other great paradoxes in math and science are not actually impossible at all, but are just waiting for someone to draw the right picture?